Hey Jan, thanks for the time. I put together a small MVP of the kind of system I had heard described in our technical brief. It's a deterministic clinical reasoning engine with an LLM layer bolted on as the boundary. And the app I'm about to walk through is driving a real functional medicine protocol running on Fast API Service Backend by Aurora Postgres. I'll go through it as a clinician would first, and then I'm going to pop open the admin view to show what's underneath. I'm anticipating this will be roughly 8 minutes. And then I'd love to hear where I'd made different calls in your production context. So let's start with the intake wizard. The entry point isn't a raw form with hundreds of fields. It's a short guided wizard, and every step maps to exactly one clinical concept. And every input the clinician enters here is going to become a typed event on an append-only timeline. And I know this is something we talked about before. But they don't need to know that yet. The clinicians, that is. And so we're just going to click through these menus. And these aren't generic EHR fields. Functional medicine, as you very well already know, relies on a specific panel. Things like zonulin, Dutch, cortisol, LPP, Dow. And the UI uses their real names and units. Any rigid template that forces a clinician into ICD-10 only categories is just throwing away the signal. And so let's make this a bit higher. We're going to go with 3.2 here. Okay, and then we're going to submit. And so what we can see happening is that the patient got routed. The engine took 4 deterministic transitions to land here. It was intake, order labs, await, leaky gut protocol. And none of that branching was encoded as if statements inside the app. It all came from the data, and I'll show you that in a minute. So if we look over at this zonulin at 3.2 ng/ml, it's elevated. Each finding is rendered in a clinical language with threshold context. So the elevated badge isn't computed in the UI. It comes from the schema definition of what elevated means for that biomarker. That's so if the reference range changes, there's one place to edit it, not 30 template files. And if we scroll down to the journey list, this is the session's full history. It is append only. The current step you see at the top isn't stored anywhere as a field. It's a projection of this timeline. And what that means is undo, audit, replay, and corrections stop being 4 different features and become the same mechanism. You just add another event and recompute the projection. Now, this is something similar to what we did at Gravity for big data. You just record every possible event. It is useful in many more ways than just this. So again, every transition you see, move to order labs, move to leaky gut protocol, it's recorded as its own event with the rule ID and the from and to pair. And that's the audit trail. So when a regulator asks, why did the system decide this? The answer is literally right there. Now, I know I'd mentioned some ternary logic before, and this is one thing that you didn't see in the front-end UI. So while the patient was on await labs without a zonulin result, the engine didn't fall through to a default. Evaluation would return unknown when the data is missing, not false. So the patient stays parked instead of silently routing through a fallback. As we can see, the lab came back negative, and the lab hasn't come back are fundamentally different things, right? So that's worth repeating. So the lab came back negative, and the lab hasn't come back are fundamentally different states. And collapsing them into like a single Boolean is how we'd get silent misrouting. So something else not demonstrated but worth calling out is that events have 2 time fields. We have SEQ, short for sequential, for insertion order, and then a timestamp for clinical time. A lab drawn 3 days ago, but arriving in the inbox today sorts correctly in the derived facts by the clinical timestamp. And so async labs become a non-event. Let's see what else. So if we switch over to this other tab here, this is the admin protocol view. And we have 9 nodes and 9 rules. And so it's the same protocol that a clinician just walked through, but rendered as a graph, the graph that it actually is. And so each box is a node and each arrow is a rule. And the nodes, shapes, and code kind. So we have rounded ones for actions. We have diamonds for decisions, and then double circle for terminal. So you can see the protocol's topology at a glance. And then if we go a little bit further down, we have our rules list. And we can look at any rule, like, for example, we can look at zonulin elevated. This is the most important slide in the deck if there were slides. Every rule here is a data record and not code. So you have this pattern of source mapping to target, condition tree, priority for tie breaking, and a clinical ops person can then edit this in a JSON file and even version control it. So we can round trip through a database. We can diff to protocol versions. And critical for healthcare, we never eval a user-authored expression, and that's a security boundary, not a performance one. So going back to the zonulin elevated, if we look at that, we can see that it has a priority level assigned to it of 20. I'm a big fan of having priorities on things, as you knew when we talked about some of the other systems I built, but we can see it's elevated, and it routes specifically to leaky gut. So if a different rule were to, say, fire for the same node with a lower priority, it would become a loser, and then the loser is logged on the transition event. And so then we're able to answer, why did this rule win in SQL, if we wanted to do so. Now, if we look at the functional medicine thing here up at the top, we see how there's that V1. That's not cosmetic. Sessions pin the protocol version they were created against. So this is useful because if a clinician edits the protocol mid-flow, existing sessions raise a graph drift error. And that's instead of silently applying new rules. And it's a cheap upfront decision that's very expensive to retrofit. What else? What other points do we want to touch on here? So the LLM layer is not surfaced in the product UI yet, but I don't want to gloss over it. So if we hop over to the source code here, the core thesis I defend in any room here is that the LLM should not make clinical decisions. It is simply a translator from unstructured input to the type schema that deterministic engine already understands. And so the rules engine under this paradigm will stay auditable and the LLM stays bounded. Everything in this module is in service of that single sentence, right? It does not make clinical decisions. So if we look a little bit further, we have our three classes, our extractor, our router, and explainer protocols. And these are some of the primary modalities of what the LLM is going to be doing. These are the roles that it takes. And when there is no static rule matches for the router, it would suggest a next node from a closed candidate set, and it's never freeform. For the explainer class, after a deterministic transition already fired, we render it into the provider-friendly language. And then lastly, we have the explainer, and this is going to be a read-only. And so none of these three have authority to change engine state directly. They all go through the validator. And so then you can see that we have this validate extractions function and a validate routing function. I'm just going to skim. You can pause if you'd like to at these parts. And then, so we have 4 guardrails. Fail closed. So on any subthread threshold extraction in a batch, like partial ingestions is the most dangerous failure mode in clinical data because it looks right. We have closed world outputs on routing. So an LLM can't invent a node ID or escape the allowed set. And then we have pydantic validation at the boundary and provenance. So every event produced from an LLM extraction carries provenance is equal to LLM extraction, as you can see in the parameters, and confidence on its payload. So the audit knows which fact came from a model and how sure it was. So I've got a little bit of spare time here, like maybe 10 to 30 seconds. And one of the things that I wanted to talk about was I'd mentioned hyperbolic embeddings. So, should I talk about those? Yeah, why not? I'll try to keep it brief. So, on the retrieval side, when you're actually trying to get information, I just wanted to mention that in a standard RAG system, they typically will embed medical concepts in what's known as a flat Euclidean space. But I think that in functional medicine, where there's a lot of taxonomies, symptoms to biomarkers, to systems, to root causes are a tree-shaped type of data. And they can have exponentially many leaves per parent. And so if you were to eventually get to an embedding retrieval system, the Euclidean embeddings would distort the parent-child geometry at depth. And so what that means in real terms is that you can get hallucinations that look semantically plausible but are like structurally wrong. And so At some point down the line, I think that like there's a really great opportunity for us to productize and incorporate into this system that we're building for providers a hyperbolic embedding space for information retrieval. I'd be more than happy to talk about that if we decide to move forward. But this is pretty much everything I wanted to cover. Thanks for your time.